The construction of large-scale infrastructure projects often relies on specialized machinery designed for immense tasks. One such extraordinary piece of equipment is Martina, the world's largest tunnel boring machine, TBM. Weighing an astounding 4,500 tons, this behemoth is not only an engineering marvel but also a showcase of technological advancement in tunnel construction. Martina's impressive size and capabilities were put to the test during the construction of the Sparvo Road Tunnel, part of the Variante di Valico Highway, A1 in Italy. Martina, which was specifically designed for the Variante di Valico project, boasts a cutter head diameter of 15.6 meters, making it one of the largest in the world. The term cutter head refers to the rotating part at the front of the machine that excavates the tunnel face. The massive size of the cutter head enabled Martina to handle the wide cross-section of the Sparvo tunnel, which is crucial for modern highways to accommodate multiple lanes and extensive support infrastructure. Weighing over 3,000 tons, Martina is a highly sophisticated piece of equipment, engineered to dig through the Apennine Mountains' complex geological strata. The tunnel boring process was made more challenging by the variable rock types and the need to maintain precise alignment while ensuring safety in the tunnel. A remarkable part of Martina's journey involved a complex and innovative U-turn rotation. During the project, the TBM needed to be rotated 180 degrees to move from the North Tunnel to the South Tunnel, a feat that had never been accomplished at this scale before. This maneuver was essential for the machine to continue boring in the opposite direction without dismantling or transporting the equipment overland, a time-consuming and costly procedure. U-turn operation using hovercraft technology. The U-turn operation was executed using hovercraft technology, a groundbreaking approach developed by Toto Costruzioni Generali and the Palmieri Group. This innovative technique employed air cushions, much like a hovercraft, to lift and rotate the massive TBM. The air cushions enabled a smooth and controlled movement, allowing the rotation of the 4,500-ton TBM without causing damage to its components or the surrounding infrastructure. The hovercraft-inspired system, known as the Air Mover 3000, was an air cushion-based carrier system specifically designed to handle Martina's enormous weight. It utilized a network of 80 air cushions, each with a lifting capacity of 43.5 tons. These cushions, measuring 10 meters by 12.5 meters each, were arranged under the TBM to provide balanced lifting and movement. The Air Mover 3000 system was central to Martina's successful 180 degrees rotation. Its modular design allowed the system to be configured in various ways to accommodate the unique structure and weight distribution of the TBM. With a total lifting capacity of 3,200 tons, this air cushion system provided both stability and flexibility. The concept behind Air Mover 3000 was to create a floating effect for Martina. By inflating the cushions with compressed air, the machine could be slightly lifted off the ground, reducing friction to a minimum. This facilitated the U-turn maneuver, which was completed in a record time of 15 days, an impressive feat given the complexities involved in repositioning such a massive machine. Backup wagons for efficient operation to support the main TBM unit. The project also employed several backup wagons, which played a vital role in housing various components essential for the operation. These wagons followed behind the TBM, carrying equipment, cables, and other supplies necessary for continuous boring. Wagon 1, weighing 550 tons, it housed critical support equipment for the boring operation. Wagon 2, at 360 tons, this wagon carried additional supplies and machinery needed for the excavation. Wagon 3, weighing 180 tons, it served as a supplementary support vehicle for the TBM. These wagons were crucial in maintaining efficiency, ensuring that Martina could operate continuously and that the logistical challenges of the project were minimized. The Sparvo Tunnel and the Variante di Valico project, Martina's impressive capabilities were demonstrated during the construction of the Sparvo Road Tunnel, a key part of the Variante di Valico section of the A1 highway. The Variante di Valico project aimed to upgrade and expand the highway running through the Apennine Mountains, one of the most critical transportation routes in Italy. The Sparvo Tunnel, in particular, was a challenging section due to the complex geology of the region and the need for a large-diameter tunnel to support modern traffic demands. The successful completion of the Sparvo Tunnel not only highlighted Martina's engineering prowess, but also showcased Italy's commitment to advancing its infrastructure with cutting-edge technology. By reducing travel time and improving safety, the Variante di Valico project stands as a significant achievement in Italian civil engineering. The innovative use of hovercraft technology for moving and rotating the TBM Martina is a testament to the growing role of advanced engineering solutions in modern construction projects. This achievement opened new possibilities for the efficient handling of large-scale machinery in challenging environments. By demonstrating the feasibility of a 180 degrees rotation for a massive TBM, the project paved the way for similar applications in future tunnel construction endeavors worldwide. The story of Martina, the world's largest tunnel boring machine, is a remarkable example of engineering excellence and ingenuity. The machine's ability to dig through challenging terrains and undergo a complex U-turn rotation exemplifies the advancements in civil engineering and technological innovation. The Sparvo Tunnel project, as part of the Variante di Valico highway upgrade, was a demanding endeavor, requiring the coordination of highly specialized equipment and cutting-edge techniques. With its 15.6-meter cutter head, air cushion-based carrier system, and modular backup wagons, Martina was not just a TBM, but a symbol of engineering ingenuity. The use of Airmover 3000, with its hovercraft-inspired technology, allowed for the seamless repositioning of this massive machine, saving both time and resources. The successful U-turn maneuver and subsequent continuation of the tunneling process underscore the importance of embracing innovative approaches in large-scale projects. Martina's story will undoubtedly inspire future projects to push the boundaries of what is possible in tunnel construction, marking a significant milestone in the evolution of TBM technology. From its groundbreaking design to its revolutionary handling techniques, Martina represents a convergence of mechanical prowess, precision engineering, and cutting-edge technology. This achievement not only marks a milestone in tunnel construction, but also serves as a shining example of how human ingenuity can overcome monumental challenges to build a better future. Tunnel boring and the operation of a tunnel boring machine, TBM, the construction of tunnels, has been essential in facilitating the movement of people and goods, playing a key role in the advancement of civilizations. From the beginning, humans have recognized that tunneling underground is the most efficient way to overcome natural barriers and shorten distances. Today, tunnels can be found around the globe, serving diverse purposes and constrained only by human imagination and the physical limitations of the Earth. BCK Public Works stands out as a global leader in tunnel construction, known for its expertise in handling projects of all sizes and complexities. Regardless of the geology, geography, or cultural context, BCK's teams have the experience to tackle a wide range of underground challenges. The process of tunneling is both a technical and human adventure, constantly presenting new challenges. Each project requires meticulous planning and precise execution due to the confined underground environment and the dynamic nature of geological conditions. Operators need both skill and humility to manage the immense power of the machinery while ensuring the safety of the team and the productivity of the operation. Several methods are employed to excavate tunnels. For shallow tunnels, a cut-and-cover method is often used. Hydraulic rock-breaking equipment equipment or explosives are typically reserved for harder rock formations. However, when it comes to creating tunnels of all sizes and through various terrains, the tunnel boring machine, TBM, is the preferred tool. A TBM is essentially a massive moving factory, weighing thousands of tons. It performs three primary tasks. It excavates, removes the debris, and constructs the tunnel in a continuous process. Some TBMs can advance several meters per hour, depending on the geological conditions and project requirements. Each TBM is custom designed for the specific terrain and characteristics of the project. At the front of the TBM, a cutting head equipped with rotating discs breaks down materials such as rock, clay, or sand. The broken down material is then transported away. This is typically done in one of two ways, either as slurry through pipelines or, more commonly, via conveyor belts. The material is then removed from the site, often by trucks, to be treated, recycled, or stored, depending on the composition and environmental considerations. One of the most critical tasks the TBM performs is the installation of segmental lining rings. These are pre-manufactured concrete segments that form the structural lining of the tunnel. The segments are assembled into rings within the TBM and are designed to withstand the pressures exerted by the surrounding ground. This lining method ensures the stability and durability of the tunnel. The precision with which a TBM operates is impressive. Using an internally developed guidance system, TBM operators can anticipate the machine's behavior and adjust its path with millimeter-level accuracy. This capability allows TBMs to navigate through complex three-dimensional routes and avoid underground obstacles. Tunnel excavation is fraught with uncertainties. There are no comprehensive maps of underground geology, and both natural and human-made structures can introduce unexpected challenges. Experienced TBM operators often rely on their intuition and skills to navigate these unforeseen conditions, particularly in urban settings where existing infrastructure must be carefully considered. In soft or mixed soils, TBMs maintain a continuous confining pressure in the cutting chamber to prevent water from entering and to stabilize the ground before segment installation. When maintenance is required in the cutting head, it must be carried out under hyperbaric conditions similar to deep-sea diving. Safety remains a top priority, and these maintenance operations are conducted with great caution. With over 500 kilometers of tunnels completed, numerous world records, and the backing of a major international organization, BCK Public Works is well equipped to tackle the challenges of the future. Their dedication to advancing tunnel construction techniques is opening up new possibilities in urban environments already packed with infrastructure. Pipeline systems are vital components of many infrastructure projects, whether for supplying water, gas, or other essential resources. Ensuring the safety and efficiency of these supply lines is crucial for maintaining reliable service and preventing potentially hazardous incidents. In the context of these requirements, INAGEN was selected for a project aimed at improving the safety mechanisms of an existing supply pipeline through the installation of a bureau-type gate valve and an overspeed valve. The installation project, awarded to INAGEN, involved the integration of a bureau-type gate valve at the main inlet point and an overspeed valve within a designated interception chamber. This strategic addition was aimed at enhancing the pipeline's safety and operational efficiency. The bureau gate valve was chosen for its reliability in regulating and isolating the flow under high-pressure conditions, while the overspeed valve was integrated to prevent surges and manage pressure fluctuations in the pipeline. The primary goal of this installation was to safeguard the pipeline system against potential risks that could arise from unexpected changes in flow speed or pressure. Two main factors were considered in this context: regulating and isolating flow. The bureau gate valve was incorporated at the primary inlet to control the flow of fluids through the pipeline and to isolate sections when maintenance or repairs are necessary. This type of gate valve is specifically designed to handle substantial pressures and flows, making it an ideal choice for critical segments of the pipeline. Mitigating pressure surges. The addition of an overspeed valve serves as a protective measure to prevent damage caused by sudden changes in pressure or flow rate. In pipelines, especially those dealing with high-pressure fluids, rapid changes in flow velocity can cause dangerous pressure surges, commonly referred to as water hammer in the case of liquid conveyance. The overspeed valve detects these fluctuations and automatically adjusts to maintain safe operational conditions. The installation of the bureau-type gate valve and overspeed valve by INAGEN marks a significant step in ensuring the safety and reliability of the supply pipeline. These components not only provide greater control over the flow and pressure within the system, but also offer essential protections against sudden changes that could lead to system failures. The chambered installation design allows for straightforward access for monitoring and maintenance, ensuring the longevity and continued efficiency of the pipeline. This project demonstrates the importance of proactive safety measures in critical infrastructure, highlighting how the strategic installation of key components can significantly enhance the operational resilience of pipeline systems. The success of INAGEN's installation will undoubtedly serve as a model for similar safety upgrades in supply pipelines elsewhere. The Limmern Pumped Storage Plant, part of the Unveiled 2015 project, is one of the largest and most ambitious energy expansion efforts undertaken by Axpo, a leading Swiss energy company. Located in the Swiss Alps, this project aims to increase Switzerland's energy storage capacity through the construction of a new pumped storage facility, which moves water between Lake Limmern and the Mutsee, located 630 meters higher. This height difference is crucial for generating electricity during periods of high demand. The Limmern and Mutsee lakes are situated close to one another, but the significant altitude difference between them creates an ideal setting for a pumped storage facility. Despite the proximity, Mutsee's existing size was insufficient to support the economic and operational requirements of the plant. To address this, a new dam was built at Mutsee to triple its storage capacity, transforming it into a key component of the new Limmern storage system. The dam, over 1 kilometer in length, is the first new dam to be built in Switzerland in 30 years. Axpo's construction site, at an altitude of 2,500 meters, is Europe's highest, presenting unique logistical and environmental challenges. Unlike an arch dam that leans against steep mountain flanks, the Mutsee Dam was designed with a triangular cross-section and wide base, allowing it to withstand the water pressure through its own weight. This type of structure, known as a gravity dam, required a massive amount of building material. Most of the construction material was sourced from the rock excavated during the creation of underground caverns. The material was transported up the mountain using a specially designed cable car system, which made over 20,000 trips to deliver the necessary rocks. Once delivered, the material was processed and sorted in an on-site facility and stored in silos before being used to produce different types of concrete. The dam was built in 68 individual blocks, each 15 meters wide. To streamline construction, every second block was initially built, using the existing sidewalls as molds for the adjacent blocks. These blocks were interconnected through openings in their side walls, ensuring a stable and continuous structure. Before construction, the site was excavated to expose solid bedrock, which was examined by geologists and prepared with specialized concrete to fill any cracks or faults. The construction of each block took place in 3-meter-high layers. The concrete formworks were precisely aligned, and the concrete was poured in 50 centimeters increments. Each increment had to be spread and compacted rapidly to ensure a perfect bond between layers. Cooling pipes were installed at the base of larger layers to prevent the concrete from overheating and cracking during the curing process. Given the size of the dam, construction involved carefully orchestrated logistics. Mobile cranes transported the heavy concrete buckets to the site, each weighing up to 17 tons. Since the cranes had to be positioned directly at the construction site to handle this weight, precision and coordination were essential. The dam's highest blocks reached heights comparable to a 10-story building, and constructing these narrower sections presented even more challenges. The construction site's high-altitude location made weather a constant concern. Unpredictable conditions, including sudden fog and the threat of early snow, meant that work had to continue around the clock, regardless of daylight or weather conditions. The team worked in 24-hour shifts to ensure steady progress, especially as the winter season approached. Despite the challenges, 2013 saw favorable weather, allowing for significant progress between spring and autumn. By November, construction crews poured the final concrete layers of the year against a backdrop of snow-covered peaks. By the end of the construction season, the dam was completed according to the schedule, with only the crown of the dam left to finish in 2015. The construction of new rail tunnels under London for the Crossrail project began in 2012 and was completed in May 2015 with the breakthrough of the last tunnel boring machine, named Victoria, at Farringdon. This ambitious project involved 8 massive tunneling machines, each weighing around 1,000 tons, which together bored a total of 26 miles, 42 kilometers of tunnels. These tunnels have a diameter of 6.2 meters and run beneath central London, marking one of the most significant infrastructure projects in Europe. Crossrail is set to increase the capacity of London's rail network by 10%, enhancing connectivity across the city. Once fully operational, it will serve 40 stations, linking key locations like Reading and Heathrow in the west with Shenfield and Abbey Wood in the east. Services through the central London sections are expected to start in December 2018, aiming to accommodate approximately 200 million passengers annually. The scale and complexity of this project have been recognized globally, with Crossrail winning the prestigious Judges' Supreme Award at the 2015 New Civil Engineer International Tunneling and Underground Space Awards. The successful completion of the tunneling phase marks a significant achievement in urban engineering, showcasing advanced tunneling techniques and careful planning to navigate London's busy underground landscape. In addition to its impact on transport, Crossrail represents a major engineering triumph, demonstrating how large-scale infrastructure can be executed in densely populated areas. Once complete, it promises to revolutionize travel within London, significantly reducing journey times and providing a more efficient and reliable rail service to millions of passengers each year.